Hi, I'm Tanmoy. Yeah, I'm Tanmoy Mondal. So currently I'm working in a team called Zenith in India. So it's in Montpellier. So the work what I will be presenting today, it is the work I did in my previous postdoc, what was in La Rochelle in France. And the work was mainly on binarization. So there was a paper submitted in last IGDA, and it was accepted. So, and this work was concerning about this paper in last IGDA. So here we will be discussing about the binarization of historical documents, and then I will show you some results on papyrus documents also. So I try to make this presentation, so I hope that I can explain what we do in computer science a little bit in layman way, so that my colleagues here who are not from computer science, who can understand a little bit that what is going on and how we do this processing. So there will be some technical stuffs what I will not go into details. So my computer science colleagues, please pardon me. I will maybe repeating the same things you already know. But it's mainly, the objective is to make it understandable for everyone. So let's start. So here the algorithm outline, what I will be discussing in detail a little bit. And the objective would be to again explain it for non-computer science people. How the binarization is done on document images, historical document images. And again, the binarization of what I will be talking about today, it's non-training based. So non-learning based, because from the very first day, we have been listening a lot of training-based algorithms where you need a lot of data. You need ground truthing, which is very expensive. So that's why we come up with some idea that without any training data, how can we do a good binarization? Maybe it is not that good as training-based binarization, but again, the advantage is that you don't need some ground truthing. So I'll be explaining the details of the I'll be explaining the details of the algorithm. So these steps I'll be explaining one by one, and then I'll be talking about the results, and then I will show some results on papyrus dataset. So here is one simple example of papyrus data. And this is the ground truth. So those who don't know what is ground truth is a very difficult and very tedious process where you need to ask some experts from the domain of history or crypto papyrus, that you ask at least 4 to 5 experts, ask them to say each pixel of an image, whether it's text or whether it's background. So if your image is of size maybe 500 cross 500, very small image, so you have kind of 25,000 pixels to do labeling. So and if you do it for with 5 users or 5 experts, it's a huge task. Okay? So that's why the objective. So this is a ground truth, and this ground truth is needed for mostly all those training-based documents, all those training-based or learning-based systems for binarization. And that's why it's always better to avoid if we can. So, and the objective is that to get a binarized image, which should look like this. And this is an example of binarized image, which is non-training-based binarized image, where you can see that there's a big there are some difference with the ground truth. Here is the ground truth, and here is your binarized image. So it will not be perfect, but it will give you something. Okay? So the objective would be to improve this image as much as we can, which could be as close as the ground truth. This is the final objective, and if we can come as close as to the ground truth, we are the winners. Yeah. So this is the objective of every image processing guys working in document images in the domain of binarization, to be close to the ground truth as much as he can. Okay. So now I'll be giving you some small concepts of image processing. to understand the algorithm a little bit later. So again, to make it very simple, I will be using one concept which is called connected components, and everyone in image processing who use it. What is connected component? It is very simple thing, like you have, why it doesn't work? Like you have several components here, like several blobs you can see. And when someone asks you that, find me connected components, you give them like the components or the blobs which are connected together but separated. So you can see that here there are some components which are connected together or which are closer, like which are in the neighborhood, but each components are separated. So they are marked by different colors. Okay. So this called connected component in the concept of image processing. And then again in this third image, you can see that some of the components we removed based on the size of the component of the component. So for example, there are some components which are small, so we can easily remove them based on the size of the component. So here this is calculated by finding the pixels which are connected in the neighborhood. So this is one concept, and the another concept I'll be using later is that this is an image which we call gradient image. So gradient image is basically that you have an image, and you try to find the edges in the image. Okay? So we can see that you have an image like this, and you apply some kind of processing on the image, and where you can find the edges in the x direction. X direction means in the horizontal direction. Here you have the images in the you have the edges in the y direction or the vertical direction, and when you combine both of them, you get an image with edges. So that's the objective of doing some gradient or some processing which we call gradient operator in the image processing concept. So here, so this is the gradient operator to find the edges in the images. Now I will come to the topic of my algorithm. So this algorithm will be, so this is the some building blocks of the algorithm. I will be explaining each of the block separately. So you have the document image. And from the document image, you try to find the width of your characters, the character strokes. And then you also find some technique to remove the background from the image. And then you use some techniques to find the gradient, that means the edges from the image. You do some clustering to find those pixels which looks similar or which has a similar kind of colors. And by combining all these things, you do the binarization. So to find the stroke in the image, what we do is that you have an image like this, and you do some processing so that the image would be enhanced, and the edges would be more visible. So you do some processing so that the edges would be more visible and from the background. And this is like a image, like enhancing the contrast of the image, kind of with some extra processing. So you try to find the edges in the image. After that, here these are some other processing in the image where you do some binarization, like simple binarization on the image, and then you get those edges more clear. Okay? And then using those edges, then you try to find that what are the width. For example, you have this kind of edges. So you try to find that what are the width of these edges or of these strokes. Because if you go by from left to right, then you can count that how much are the gaps from one point to another point. That means what are the gaps in a stroke, or what are the width of the stroke. So you get the strokes like this, and then you get an average of the strokes. So that will give you the stroke width, average stroke width of the characters in the image. Okay. So after finding the stroke width of the image, then the next task is to do the removal of the background from the image. Because if you can see, the image was quite noisy. This is not that noisy, but we will be having some images which are very noisy. So the objective is another objective is to remove the background as much as we can, so that we can have a clear image from the noise or background. So here also we use some processing to generate one mask. And using this mask, we move over the image. And the objective is to calculate iteratively the background of the image, so that we can remove the background from the original image and we can get a clear image. So here are some processings we do by using the mask I showed you. So, and by using this mask, we can clean the image. And here you can see we can get a better image, which is more clean than the original image. So it is done by removing the background, because the objective is to calculate a background. So you subtract the background from the original image, and then you get a clearer image. So that same process is applied for Papyr's dataset, and I will give you one example. So you can see the difference, what it gives you. So this kind of noisy images it was, and when you remove the background from the original image, it gives you quite clear and quite, sorry. Yeah, it gives you quite clear images, which is easier for further processing. Okay, so that's what we do with the background removal of the original image. So now we have the stroke width of the characters in the image, and we have the background removed image, which is more cleaner. So now we have the stroke width, and we have the stroke width, and we have the background removed image. Now the next task would be to introduce one concept, what is known as structural symmetric pixels. So the idea is that if there is a text in an image, so the text image, the pixels around the stroke, which contain both text and background pixels. So for example, here you have an image, and if you find the edge of the image, so this edge of a text, around the edge you will have some background image and you will have some text image. That means this side you will have some background, and inside this side you will have some text portion. So this concept is used to identify the text pixels from the non-text pixels. from the background. And this concept is called structural symmetric pixels. So the structural symmetric pixels will have large gradient, and it will have a large magnitude. So what you can see is that if these are the pixels at the border, which we call as structural symmetric pixels, the characteristic of this pixel would be that it will be have gradient directions which will be opposite. So gradient direction means that every pixel will have some orientation. So the orientation of the pixels should be opposite, and the pixels would contain at its neighbor the text and non-text pixels. So this characteristic of border pixel or structural symmetric pixels we use for finding or for distinguishing the text and non-text pixels. So here, this is the processing we used also for cluster out the real image into some different cluster. And here we use a concept called fuzzy Siemens clustering. So the concept of fuzzy Siemens clustering is basically it clusters out the pixels which has a similar kind of textures or similar kind of color values. So here you can see that if we apply a clustering algorithm on an image like this, it will generate different color of clusters. So from here you can see that those color which are completely black, we are sure that they are text pixels. Okay? And after that, when you will see that there are some pixels which are not we cannot completely say that they are text or not. So these pixels are this kind of like gray pixels, and there is another shade which is this kind of shade which is lesser gray but not completely white. So there are two class of pixels which are, we call it here confused pixel, because we don't know whether they are text or they are not. They are like non-text pixels. So that's why we use some further processing to understand or to correctly say that these are text or non-text pixels. But for these black pixels, we are completely sure that they are text pixels. So here the task is to find whether these two class of pixels are text or not, because we are very sure about the black ones. So if we just put the black pixels, it would the binarized image would look like this. But then if we add the pixels which were gray like this, and if we add those pixels, the binarization results would little bit improve. Okay. And then if we add the third clusters, which were lesser gray, the binarization result will improve more further. Okay. So now, this was just these were the results where we just put those confused pixels and like one by one and see that whether these confused pixels, adding these confused pixels are good idea or not. But there are no checking until we have done that to be sure that these confused pixels could be taken as text pixels or not. Okay. So for that, we do certain amount of checking and certain amount of verification based on some idea that a confused pixel should be surrounded by many SSP kind of pixels. For example, if we do some edge detection technique on this image at the left, it will give you some edges like this, and this kind of pixels would certify that whether these pixels in the clusters are actually the text pixels or not. Okay. So by using some characteristics or by using some features of these pixels, we confirm that whether these pixels are actually text pixel or can be classified as really text pixels or not. So we use the criteria of density, that how many of these pixels are surrounded by this kind of confused pixels. If this kind of SSP pixels are high in density around the confused pixel, then we can say that these confused pixels could be text pixels. Okay. So this is one sort of criteria we have used here to classify the confused pixels in text pixels. And there are another criteria we used regarding the orientation of SSPs around the confused pixels. So again, there was one concept used by Imran regarding the defining the orientation of each SSP pixel and dividing into them different beans. So here you can see that the beans are defined. For example, we have defined 8 beans, and the orientation from 0 to 360 degree are divided into 8 beans, and we find that how many pixels around the confused pixels are actually surrounded by how many pixels which have the similar kind of gradients. And again, this gradient criteria also used to recheck whether the confused pixels can be classified as text pixels or not. So and another idea, and then another more criteria is based on threshold of the SSP pixels, which are third criteria to use are used for classifying the confused pixels as text pixels or not. So based on these 3 criteria, we finalize that those confused pixels could be classified as text pixels or not. So there are some results on some data set from historical data set, which is DeepCo data set we have used, and there are some comparison table. I will not go into the details of this. I will show you quickly some results of on Papyrus data set. So you can see, for example, this was the original image. And if we compare from the ground truth and the result image, we are not very far. So there are some artifacts and there are some noise still exist in those in our results, but we can improve a bit further by again by removing those small components which can be removed by based on the size. So some more results, and thank you.